Let us now discuss on flow system asymmetries and principles of energy conversion. Our first basic principle of energy conversion or extraction from the environment can be simply enunciated as energy can only be extracted from a flow system. Energy can only be extracted from a flow system. A corollary that can be drawn from the above principle is the energy flow is from high energy storage reservoir to a low energy sink. The energy flow is from a high energy storage reservoir to a low energy sink. Totally blocking a wind stream does not allow efficient energy extraction. Only by allowing the wind stream to a flow from a high speed region to a low speed region can energy be extracted by a wind energy converter. That means if you block the flow of wind, you cannot extract the energy from the flow of the wind. The energy can only be extracted if you can let the wind flow. A second principle can be stated as only the asymmetries in a hydraulic, kinetic, thermodynamic or aerodynamic system allow the extraction of a portion of available energy in the system. Ingenious devices conceptualized by ingenious people take advantage of naturally existing asymmetries. Alternatively, ingenious artificial configurations or situations favoring the certain of these asymmetries are created so as to extract energy from the environment. A third principle is that the existence of a flow system necessitates that only a fraction of the available energy can be extracted at an efficiency characteristics of the energy extraction process, with the rest returned back to the environment. In thermodynamics, the ideal heat cycle efficiency is expressed by the Carnot cycle efficiency. In a wind stream, the ideal aerodynamic cycle efficiency is expressed by Bethe efficiency equation. In the last section, we have already understood how energy from flowing wind can be converted into some other form, mainly electrical energy. Now we will understand that what is the efficiency. That means what percentage of input energy may be converted to the output by a turbine. In this case, we will talk about Bette's law, but this is somewhat very much related to Carnot's law also. Was Carnot's theorem stated in thermodynamics that energy only can be extracted when heat is flowing from higher temperature reservoir to lower temperature reservoir. In case of wind flow system also, we have seen that energy can be extracted from wind when it is flowing from, say, higher velocity to lower velocity. When it is flowing, then only it can be extracted. There is a similarity. So what Bette's law is saying, Bette's law is analogous to the Carnot cycle efficiency in thermodynamics, suggesting that a heat engine cannot extract all the energy from a given hot reservoir of energy and must reject part of its heat input back to the environment. Whereas Carnot cycle efficiency can be expressed in terms of Kelvin heat input temperature T1 and the Kelvin heat rejection temperature T2. This is somewhat, you know, that eta Carnot equal to T1 minus T2 whole by T1. or equal to 1 minus T2 by T1. This you know that. Bates equation deals with the upstream from the turbine wind speed V1 and downstream wind speed V2, and the efficiency is somewhat like this: V1 minus V2 by V1. The loss of energy or the loss in efficiency of heat engine is caused by heat rejection to the environment. You know why? Carnot engine also, which is an ideal mechanical engine, cannot reach the efficiency up to 100%, because you cannot avoid loss of heat to the environment. Cannot avoid. Think about any say coal engine. So when you are burning the coal, you cannot convert all the energy to the mechanical energy, because some portion of energy will be used up for heating the engine, for heating the environment. Some will be radiated out. So you cannot avoid it. You can stop it. So the loss in efficiency of a heat engine was caused by the heat rejection to the environment. The losses in the efficiency for a practical wind turbine are caused by viscous drag on blades, the swell imparted to the air by the rotor, and the power losses in the transmission and electrical system. We have seen that from Bates equation we have got that total power you can find out later on the calculation, and whatever soft copy of in class note you will get there, the whole calculation is given. That is a completely mathematical one, and this is quite self-explanatory. So there you will get that P total power you will get out of a turbine, maximum power, that is 16 by 27 into half rho S V1 cube. This is half rho S V1 cube. This you have seen earlier, we have discussed earlier. This is the input energy given by the wind to the turbine. So you can see the maximum power that this turbine can convert into the output power. The maximum fraction is now 16 by 27, which is equal to 0.592593, or you may say 59.26% max. 59.26% of input power can be converted to the output. So the maximum power content here is nothing but 0.59, and this is Bates coefficient. Now we will understand some very much required terms which we will be using in the following portions, and that are three different speeds related to turbine. The first, we must know about cut-in speed. Cut-in speed is that speed below which the wind basically cannot generate any power. So the cut-in speed is very simple. It's the point at which the turbine starts generating electricity from turning. Rather, the cutout speed or somebody says cut-off speed is somewhat more important though, and denotes how fast the turbine can go before wind speeds get so fast that it risks damage from further operation. Means how fast the turbine can rotate with wind, avoiding damage. The primary safety issue with the wind turbines comes from overspeeding. So some sort of stall or brake mechanism is needed to shut down the turbine before it reaches the danger zone. Most turbines have a rated peak speed. Rated peak speed means where in that speed where you can get the maximum power output, optimum power output you may say. That is a wind speed at which they will return the optimal amount of power. Wind speeds both lower and higher than this speed, That means wind speed, if it is greater than the rated peak speed or it is less than the rated peak speed, whatever it may be, are likely to produce less energy. So the output of the wind turbine will depend on what kind of wind speed is rated for. Now let us understand some very important terms and important thing about the turbines, which will help us to understand the working of turbines, different types of turbines. These are the parts of the turbines, some basic parts, very basic parts. The principle behind wind turbines is very simple. The energy in the wind turns the blades around a rotor. The rotor is connected to the shaft, which spins a generator to create electricity. Here, basically the mechanical energy or rotational energy transforms into electrical energy using the principle of dynamo. Wind turbines are mounted on a tower to capture the energy from wind. Now, the higher the blades are, that means more is the height, okay, where the blades are fashioned. The higher the blades are, the more they can take advantage of faster and less turbulent wind. Because at higher height, there is less disturbance, so less turbulence will be there. So higher the blades are, the more they can take advantage of faster and less turbulent wind. A simple wind turbine consists of three main parts: the blades, shaft and generator. Now let us understand their functions. What is the function of blades? The blades act as barrier to the wind. When the wind forces the blade to move, some of the wind energy is transferred to the rotor. Now what is the function of shaft? When the rotor spins, the shaft also spins, as the shaft is fashioned to the rotor, and hence it transfers mechanical energy into rotational energy. Next, what is the function of generator? A generator uses the difference in electrical charge to produce a change in voltage. Right? This is very, I don't need to explain it because you very much know the principle of dynamo. When some, coil is rotated in a, magnetic field, what happens? According to the principle of electromagnetic induction, the electrical energy will be generated in the coil. The same principle. So voltage is actually electrical pressure and force that moves that electric current. The voltage drives the electrical current through the power lines for distribution.